things for the last, I don't know, couple months or so. I've been working on some neural network pruning. So we have a blog post, and a lot of what I'm sharing today comes from the blog post, or at least is sort of background for that. So you may have seen it. And anyway, again, feel free to stop and ask questions anytime. So first question is, what's happening inside of a neural network? So we want to understand what pruning is. We have to sort of understand what's going on inside. And so every neural network is going to have some input. And so if you're talking about images, that's a block of numbers. Right? So if you think about it as an image, whatever. The computer sees it as just a 3D block of numbers. It's going to go through some function and produce some other block of numbers. Doesn't really matter what those are. And then it's going to go through another function, produce another block of numbers, and it just sort of iterates and iterates and iterates. And what those functions are doesn't matter so much. And exactly what they're doing doesn't matter so much. I mean, and how many of them you have, right? These are all sort of questions that are involved in designing the architecture of the network, something I did in a previous life. But for the rest of this talk, we're just going to assume that you already know what those functions are and that the sort of shape of the network is already set for you. One of the common layer types or functions that you'll hear about is called convolution. Okay, and what convolution does is you have, again, a block of numbers that's your input, and you'll have a kernel. People call them a variety of different names, kernel or filter or whatever. The key point is that that's a pattern. And so what convolution is doing is it's sort of looking all over your input for that pattern. And it's sort of scoring how well does each region of your image reflect that pattern. Okay, so when you sort of scan over the image for that pattern, you produce some map, and that map is, again, just a block of numbers. Right, but the point is that if you have one kernel, then you sort of learn how common that one pattern is. But most of the time, you're going to have multiple kernels, and so you're going to be looking for multiple different patterns, right? And what a convolution layer is going to do is it's going to have a bunch of kernels or patterns that it's looking for, and it's going to produce a block of numbers. Sort of each slice represents a pattern, or the presence of a pattern. Okay. And that block of numbers is what gets fed into the next layer, and so on and so on and so on. So these kernels are what we call learned weights, and so that's the sort of flexibility of your network. And again, it's block of numbers, but that's the bit that you're learning, and then the output is what's being computed. Okay. So what does it mean to prune a network? So you can imagine a convolution layer here, and it has a whole bunch of kernels, and it's producing this output. Well, all pruning is identifying some kernels and getting rid of them, right? That's pruning. So you can kind of see what's going to happen is you're going to reduce the number of learned parameters in your model. Because you don't have to compute those sort of feature maps, it's less computation. So it's sort of simplifying your model. And oops, wrong direction. Okay, so what problems does pruning aim to fix? So true fact, just for sort of scale of what's going on here. Neural networks, at least for like vision models, typically contain anywhere from tens to hundreds of convolutional layers. Each convolution layer could have many kernels in it, typically a few hundred to a couple thousand. And each of those kernels have lots of learned weights. So altogether, you're talking about tens to hundreds of millions of learned parameters in your model, which is really kind of crazy, especially if you only have like thousands of images for training data. So you have millions of things to learn from thousands of examples.
So many convolution layers. So this is like the depth of your network, essentially. So you're saying that we're running networks that are tens to hundreds of multi-layer perceptron layers deep.
Yeah. Okay. And some models, they have like little parallel bits to them. So it's not just like straightforward, but sort of branching a little bit. And so I think the deepest models that we have where they're like convolution layers strictly in sequence are like ResNet 152, which is 152 convolution layers in a sequence, interspersed with. Yeah, so that's huge, right? And another true fact is that when you have more kernels, that requires more computation. Okay. And anytime you're doing more computation, that's going to cost you more power, more energy, and it's going to take more time to make a prediction. And both of those things are sort of expenses that you have to pay, right? And the other thing is that if you have more kernels, your network is sort of, the reason why people typically have these bigger networks is because they're more expressive. So they're able to learn more complex tasks or sort of make more nuanced predictions. And people sort of realize that, when you have a lot of parameters, you do have this sort of danger of overfitting, which basically sort of, the way to think about overfitting is it's sort of like almost memorizing your training data and not being very useful in anything that's not your training data. So that is a danger of having too many kernels. So what we want to do with pruning is we basically want to get like all the expressiveness of these really big models and be able to be accurate on challenging tasks, but we don't want to have to pay for it with power or time. So we want to have our cake and eat it too. Okay, so I guess the first question is how do you know what you even want to prune in a network? And the easiest way is just to randomly prune things, right? So just randomly pick some kernels and delete them, right? And research actually shows some of the early papers, well, I guess not the earliest ones, but some later papers show that a lot of the techniques that people had been trying for pruning weren't actually better than just randomly pruning things. And it actually turns out to be surprisingly effective, right? So it turns out these models are so over-parameterized that you can sort of cause some brain damage and the brain just recovers, right? Again, braining quotes for those of you who are online can't see the air quotes.
I mean, you were able to prune 95% of the model, so it makes sense that we could just randomly delete 5%.
Yeah, it's like you might delete one thing that was kind of important, but you can relearn that. So another thing that can happen is if you have a lot of kernels, it could be the case that you have some redundant kernels. So basically they've learned the same pattern, and so you have you recompute the same map over and over again, which is just silly, right? So just keep one of those and delete all the rest. So that's another way of pruning. The other thing is you could look for small kernels, and so there's lots of different ways to define small. But basically, the result of a small kernel is that the output is always close to zero. So basically, yeah, whatever comes in, the output's always about zero. So it's really not doing anything. So why bother computing zero over and over and over again, right? Just get rid of those. And that's the approach that we currently take. And any of these methods that I mentioned are, they'd be easy sort of extensions to add if we wanted to pursue them. But currently, we look for small kernels and we delete those.
You say almost always zero. Do you also count like usually close to zero?
Yeah. So strictly speaking, like in the math sense, what we're looking at like the maximum absolute value of an entry in the kernel. If that is smaller than epsilon, then unless your input is huge, when you do this product, the output is going to be small. And so yeah, it's not like identically zero, but it's sort of in the noise compared to the output of the other things. Okay, so that's what we do. Okay, so a little bit of a technical detail when you prune a network, right? So, a convolution produces a feature map that those feature maps become the input to the next layer, right? So when you delete a kernel, right, now instead of producing, in this case, we were producing 9 outputs, and then we delete one, now we're only producing 8. Well, that next layer expects 9 inputs. So those kernels are all sort of programmed, they're set to look for 9 different inputs. And if they don't see them, then then the computer just breaks and doesn't know what to do. So the moral of the story is when you're pruning, you can't just delete things in isolation. You sort of have to look for these dependencies that are further on in the network. So in the traditional networks where it's just one layer feeding into the next, you really just have to look at one layer forward and adjust that to make sure that it's happy with the input. So in this case, what we would do is we'd take all the kernels in that next layer and just delete the section that was looking at whatever thing we deleted in the previous layer. So there's a little bit of cleaning up to do. And I said for normal networks that's not hard, but what we use mostly now, which are sort of the standard vision models, are these ResNets. And this is sort of a high-level view of what a ResNet looks like. And all of the orange blocks there are convolution layers. And you can see it's sort of organized in groups. It doesn't really matter so much. But each of those groups is what we call a residual block. And so what makes the ResNets sort of innovative is this, what they call a skip connection. So you get an input that comes into this layer. And do I have, I think. So, yeah, there was a trick. That was it. Turn on laser pointer. There we go. Oh, yeah. Okay. So your input comes into this block, and it's going to get transformed going through here. It's going to produce feature maps and then come out. But then what they do is they add to that output the input back in. So basically, your input's sort of simultaneously skipping over the block and going through the block. Okay. And what's challenging about that is now if I want to edit anything, well, okay, two things are important. First of all, if you want to add these two things together, they have to have the same shape, right? So if you're, just imagine if you're trying to add like a 2x2 block to a 3x3 block, and you're like, where do I line it up? Or like, you just can't do it. So, so that sort of created this dependency that this output size has to match the input size. And so if I start, removing feature maps from this guy, then the output size isn't going to match anymore, and I'm going to run into problems, which is, I think, outlined here. Yeah. So if something happened and it changed the size, you have a problem. So the way that we mitigate that bit is to add a little tiny convolution layer that basically is just going to reshape the input. There's a few reasons why we did this, which I think I have on the next slide. So I will save that. But anyway, so what we do is we take this network and we just modify it by inserting a little reshaping convolution layer. And we can set that to be the identity if we don't want it to do anything. So like if we already have a pre-trained network and we want to load it as a prunable model, we can set those to be the identity so that it doesn't change any predictions, and then start pruning. Okay.
Can I ask questions? This is going to be a little off topic. So the first and the second convolutional layer here, the 3x3 and the 3x3, are those shared weights or are they different weights?
They're different weights.
Okay. And then I guess, historically people would use larger convolution kernels if they're just doing image processing. And so is the idea that instead you just add more layers to your network and that's how you get effectively a larger footprint on your convolution?
I'm not sure I understand what you
mean. Like in old school image processing, 3x3 is a tiny kernel. Yeah. You might use 15x15 or whatever. And so depending on the resolution of your images and stuff. So is the answer to that you just put in more layers?
I think so, yeah. So basically like the second layer is going to be looking at the 3x3 kernel in the second layer is going to be looking at the output from sort of three side-by-side kernels in the previous layer. So so that sort of expands it. So I forget what they call that, the receptive field, yeah.
Okay. And if you look at like somewhere there's like a nice table of like common architectures and receptive fields, and they're like absolutely huge, like thousands of pixels can form, the output of a single pixel.
Okay. Thank you.
Okay, so why do we do it this way? So one of the reasons is that in 4 of the residual blocks in any of these sort of standard ResNet models, so 4 of the circles in here, there was already a little bypassing layer that followed that pattern. And the reason for that was because they're trying to increase the number of kernels that they had in that layer, or increase the number of patterns that they're looking for, increasing the number of kernels. And so they already had to have some sort of feature to bring that output shape, sort of rescale it up. And so it just sort of made sense to, well, since it was already done that way in some layers, it made sense to just sort of follow that pattern and do it in the additional layers. And the reason why we make that batch norm layer optional was for what I mentioned before, is if you want to load a pre-trained model and maintain its predictions, you can't do that if you have the batch norm, but you can if you just have convolution. So if you have them both, then you follow the pattern precisely that everything else did. And if you just have one, then so it just gives you some flexibility. And then the other reason, which I haven't given you any proof yet, but anyway, it just works. So if it works, then that's reason enough. So I haven't convinced you that it works yet, so I'll try to show you that. But the other thing I want to mention just over here about the size of these, if you're noticing here that like ResNet 34 and ResNet 50 have the same number of blocks, there are multiple different kinds of blocks, and the one that I pictured here is the simpler of the two kinds of blocks. So some blocks have 3 convolution layers, and then some have 2. Details doesn't really matter. But the point is that this number in there in the name tells you how many convolution layers, and 4 of them already have a pattern. Okay. Okay, so a little bit of proof that it works. So we took just a simple ResNet 18 model, prunable one, and we train it on the task of classifying car colors. So, look at a picture of a car, tell you what color the car is. And this is sort of what the result is from the run. So right here, if you track this orange line, we're looking at accuracy, and you can see that it's going up. And then once we start hitting these blocks, we're repeatedly just removing 5% of the model. So we trained it up to about 95% accuracy, remove 5% of the model, and keep training. And you see the accuracy actually went up a little bit still after removing a little bit of the model. Right? Then we remove 5 more percent, stays above 95. Remove 5 more percent. It dropped a little bit, but then it recovered pretty quickly. Cut 5% more out. It drops a little bit, recovers, and so on. Over here, now we've cumulatively removed 75% of the model. Delete 5% more. Those patterns are becoming increasingly important. So you delete them and it takes a big hit, but then a little bit more retraining and it recovers. So the point of all this is that we removed up to about 80% of the model, and it's still over 95% accurate. So we can remove most of that computation and still do very well. And here, we could have potentially pushed this even farther. I just stopped here because I was happy and it was taking time. Yeah. Right. So normally you might iterate this. If you had a threshold for like 95 is my minimum acceptable level. And it doesn't have to be accuracy. It could be whatever sort of statistic you care about, recall, precision, whatever you care about. If you have a minimum threshold, you can sort of keep repeating it until you don't get back to your minimum, and then just back up and take the last one that did. And eventually it will stop learning and just tank. The other thing that you could say is like, how much did this speed up, right? Because we removed about 80% of the model. So by the time we get down to 80% of the model removed, we're about 64% faster. And what that means is, here you can look at like how many images per second we can make predictions on, which is one way to look at it. And I should caveat this with this was on Lambda 2, single GPU on Lambda 2. So the speedups that you see are going to depend on the hardware that you're using. So what your base case was and what your print case is. But there's sort of a natural question, and I got asked this a lot, and so I've been thinking about it a lot. The model size, if we remove 80% of the model, what's left is about 1/5 of the original model. So why isn't it 5 times faster, right? And I don't have all the answers, but I have a couple of thoughts. So first, there are fixed costs that are not going away, and so that's reading the data from the disk, pre-processing that data if you have to, and then pushing that data onto the GPU. And that's going to be the same regardless of what your model on the GPU looks like. Even if you do zero computation on the GPU, just to do that, it's going to be the same. We thought about measuring just the time to actually do the computation on the GPU, so trying to get rid of this. That's sort of I sort of think of that as a bit of cheating, because if you're actually inferencing, you're going to have to do pre-processing and get your data onto the GPU, so it wouldn't really be a realistic picture of what you would expect to see. But again, all those fixed costs will depend on your hardware that you're using for exactly what they cost. So it's, take that with a grain of salt. The other thing is that, like, how well the computation parallelizes on the GPU. It's going to have a complex relationship with the shapes of all those blocks of numbers going through and the numbers of kernels that you have. That's all going to affect how efficiently the GPU can do that computation. So it's not always the case that if you remove one kernel that it gets faster, because you may have part of your GPU idle, for example. And then there's another of other subtleties that are involved too. So some of the kernels are more expensive to compute than others, and we're sort of uniformly deleting 5% across. I'm not sure how much that actually impacts it, but, and then let's see. Oh, and then there are also some fixed costs that are the computation that are going. I mean, I only looked at pruning convolution layers because that was where the bulk of the computation is happening. But there is computational cost in the other layers that it's going through too. And so that could have an impact. So anyway, 65% speed up is still really nice. And yeah. So the other thing I was going to say is it lets you get through like a bucket of data faster, but it also potentially gives you the option to do things you couldn't do before. So if you weren't fast enough to say do like on the fly inference, like if you have like real time data coming in and you're, then maybe this much faster is fast enough that you could do it. So that's a benefit. I would have liked to have measured sort of how much power or energy do we save doing this. I didn't really have the tools to do it. And again, that's going to be all hardware specific. So